So just to set expectations, it's called Hello Deep Learning from scratch. In the next 15 minutes, we're not gonna code up a new ChatGPT. So just to know, but we are going to study this computer program, which is 1,500 lines long. It's open source, it's on GitHub, you can read it. And even more amazingly, it can read my terrible handwriting. And this is a tool that using modern deep learning techniques, you can, in these 1,500 lines, train it to read handwriting and actually have it do some stuff and generate this wonderful image. But just to set expectations, at the end of this conversation, at the talk, we're not going to have a tool that talks to us. But we have one that will read us. So it's maybe nice. So, deep learning from scratch. This presentation is associated with a 10-chapter series of blog posts. And here I will sort of enthuse you about this series of blog posts, but it's mostly a teaser, to be honest. But I'm going to tease you really well. This QR code will come back later on even. So even if you miss it, you will have a chance to take a picture. And you will also find this exact presentation there, by the way. So who am I? Who are you? Sven just mentioned the ChatGPT revolution last year. And up to that point, I had been ignoring all the deep learning hype. Because I thought this is just too magical, this is too Californian, this is too Tesla, and it's the same people that do the blockchains. And so I decided to ignore all that stuff. And that was a bad decision. Well, it did save me a lot of time. But in November, it's like, okay, this stuff can clearly not be ignored anymore. And then I found that I needed to play catch up. I need to understand what really is going on here. As Kelsey Hightower explained in Kubernetes the hard way, I wanted to do this the hard way. And I found that it was not that easy. I hope that this presentation will also help you sort of get up to speed with what is going on for real. So you can either log into ChatGPT, ask it some questions, get some pretty good answers, but you will not have any idea what's going on. This presentation will at least allow you to understand what's going on at the very bottom of the stack. But to be clear, it's not just an example. The stuff I'm explaining here is exactly what all the deep learning stuff is doing. So this is not some kind of cheap analog. If you want to understand a rocket, think about a bottle of water. No. It's the real thing. The actual math is what I'm showing you here. So I hope that's also what you came for, because otherwise it's going to be massively disappointing. So I asked ChatGPT if it had a message for you. And I do this, well, you'll see why I do this. And ChatGPT is a sneaky bastard. So I asked it, do you have some encouraging words for software developers in the age of ChatGPT? I said, sure, your future is great. I mean, I would say that if I were threatening you. And your future is secure and promising, and the technologies are impressive, but they are tools created by developers just like you. So if I'm evil, it's all your fault. By the way, you should come to my keynote later today, which is all about evil. And it says, embrace AI. It's a self-serving bastard. And your problem-solving skills will always be in demand. Good stuff. And trust in your abilities, stay positive, and keep learning. The world needs your expertise now more than ever. Why do I post this some rather long-winded stuff? There are still people around that say, yeah, it's not a big deal, this stuff. It's just predicting the next word. No, it's a terribly big deal. It doesn't mean that it's intelligent. It doesn't mean that it really thinks your jokes are funny. It doesn't have to think your jokes are really funny. It can really do some terribly amazing things. And we cannot ignore this, because it will not ignore us. So please pay attention. So here goes. This is what you'll find online. If you want to figure out how does ChatGPT work, you have like 5,000 YouTube movies. And there is a Hugging Face, which is like a really good place where you can click and drag a cat and a dog detector together, and some really amazing things. And you can also get to work with PyTorch and TensorFlow. It's also pretty nice stuff. I'm not knocking it. These are just good things. It's just that they will only explain it down to a certain level to you. So they will say, hey, you can assemble these layers of the neural links, and this is where the cats go in, and this is where the numbers come out. But you will not really understand what it's like. And then if you want to learn more, you immediately hit some very deep academic literature or basic mathematics and matrix operations. And I'm trying to cover the middle bit. We say, well, let's see what's going on there. So I mentioned this project. Key thing is it doesn't require a GPU. It doesn't require a fancy computer. It doesn't require any dependencies. And it's code with a block. And if you start reading this and you make it to the end, then you have a decent basis for understanding deep learning. And it's really 1,500 lines. So you can sit and read it and really understand every line. So again, the QR code will come back at the end. So this is interestingly, if you really want to get a start from how does deep learning really work, or at least how does generative AI work, this is the Nobel Prize winning paper. And the people that wrote it, they also know it. And you can read it online. They didn't even formally publish it. It's even more interesting. It's still a preprint. But this one paper is the revolution that describes how does generative AI work and why can it write whole sentences to you. And the disappointing bit is we're only going to study today the little red ellipse. That's the part we can cover in the presentation here. And the rest you'll have to read up later. So first we need to say thanks to the US National Institute of Standards and Technology, because they sort of bootstrapped this whole field by generating a gigantic database of handwritten letters. This is the hello world of deep learning. Everyone starts here. And they collected, I think, 1 million handwritten letters and digits, and they scanned them, and they equalized the pixels, and you can download all this stuff, and it's great. Everyone starts with this. This is the other founder. This is Jan LeCun. He's the head of the Facebook AI, Meta AI stuff, and he's very convinced of how brilliant he is. It's impressive. I've never seen anyone so convinced of his own brilliance. But he does have a point, because in 1989, and you can find this video through the QR code I saw later, he did the demo I'm about to tell you about. And can you imagine how amazing it is that you did a whole deep learning demo in 1989, when computers were not even able to do real-time image processing. They had to first make FPGAs that could do image processing. And only then could they do a demo where they showed that the thing could read letters. So the presentation today will bring you up to this level, 1989. This is just how many digits they have, and they have a lot. And so it's nice to learn on this. What does it look like? 28 by 28 pixels of digits in this case. And this is the cleanest, nicest data you will ever find of American handwriting. And this will become relevant later on in the story. But this is a 3, this is a 7. Notice how clean the letters are and how they are exactly centered. And you cannot see it unless you have robotic eyes, but also the brightness is also standardized. So the average value of these images is all just right, which means that this is the easiest way to start doing machine learning. And let's say we want to write a computer program that can tell the difference between a 3 and a 7. It's not a massive challenge to do, but still ponder how you would program this if you would start from scratch. How would you do that? You would write a detector that would detect an angle maybe, or the thingy. But you would spend quite a lot of time on it, even by hand distinguishing a 3 and a 7. So what's the neural network deep learning way of doing this? And it's so stupid, you will not believe this, because this is a theme of this presentation. Very stupid solutions in deep learning work. So what is this solution? We take all the 3s that we have in the database and all the 7s that we have in the database, and we calculate their average. So this is the average 3, this is the average 7. And now we subtract these 2 digits from each other. So for every pixel, we're going to take the pixel in the image on the left, the pixel, the image in the middle, and there on the right, we're going to say this pixel minus that pixel is that. And you see the red bits are where there is a lot of 3 in the image. And the blue bits is where there is a lot of 7. And it's the other way around. It's the other way around. And but this is sort of the difference between the average 3 and the average 7. And you could then say, well, let's take, if we have a picture of a digit, we're just going to calculate how different is it from a 3 and how different is it from a 7. This is like the dumbest thing you could do. And well, if it's, or this is what I just said, if it's more blue, that's a 3. And is it more red, then it's a 7. So it's a very, very, very simple decision-making algorithm. Do I see more red or do I see more blue? And if you do this, it gets 97% of the digits correct. And which is embarrassing for such a stupid, simple idea. What this is will be a theme. Because straight up to ChatGPT, there are things in there where you're like, you cannot possibly do something. Oh, apparently you can. But this is not real machine learning. But you can see that it has the blues all on the left and the reds and the sevens all on the right. And apparently the score difference is sort of -4 something. And everything that has more than a 4 is apparently a 7. But we made this decision thing. This system did not learn anything itself. We helped it. We said, look, this is the difference between a 3 and a 7, and use that. Recall the number 97%, which is also already very good. And this is an example of a letter that it got wrong, a digit. This is, okay, for us it's clear that it's a 7, but you can imagine how a computer that is stupid thinks that this is a 3. And actually, depending on the context, I could also be confused if this is a 7 or a 3. Well, this is weirdly impressive, but now let's see if we can make it learn, so that we're not helping it along. Math, and it looks really good, and I think I love the math just for how good it looks. And the calculation we see here, you can write it in 2 ways. R is the result. And in this case, we said if the result number is high, then it's a 7. If the result number is low, then it is a 3. And we calculate it by multiplying the image, every pixel of the image, with this difference thingy. We said this is the difference between a 3 and a 7. And we added a bias number, which I'll get to later. You can also write this as a matrix multiplication, where you take the image as a flat matrix, and all the weights as another matrix, and you multiply that. And if R is high, we call it a 7. It's the same thing that we saw earlier, but now in math. Now let's say we're not going to help the computer. So we're not going to give it this nice difference that already allows you to see it's a 3 or a 7. We just have a random matrix in the middle. Just random numbers. So how do the deep learning people pick these random numbers? And there's some magic around that. First people said, well, let's just do between 0 and 1. Or maybe between -0.5 and 0.5. And that didn't work so well. And at one point someone discovered you need to do 1 divided by the root of the number of pixels. And if you then ask people, why did you do that? Well, yeah, it worked really well. So this is the initialization. So if you use PyTorch or TensorFlow and you initialize a matrix, it will always initialize itself to random values between minus the square root of the number of pixels and plus the square. And they have deep conversations about why this is and why it works. Just do it. And and what is the end result score? Here we see a 3. We multiply it by random. And not surprisingly enough, random comes out. And you cannot tell from this if there is more blue or more red. Really, it did not make a good decision. This result rule comes from the following formula: pixel 1 multiplied by weight 1. So the upper left pixel by that upper left pixel. And then we add to that the next pixel multiplied by the next pixel. So this is like a really long multiplication and addition. This is the formula. Now, this is a 3. We know it's a 3. And so we want the R number to be low, because if it is low, that means it's a 3. How can we make R lower? Well, we cannot change the 3, because the 3 is the 3. We can change the random values in the middle. And the way to make R go down is by making the W, the weights, go down in places where the pixel was wrong. That's as simple as that. And you do that by taking the derivative of R with respect to the weights. It looks a bit fancy, but it's just, if there's a bright pixel there and there should not be, then make the weights go down. And if there's a dark pixel there and we need no weight, well, then we'll make it, well, I have it reversed. But it's as simple as just rotating the knobs. Just changing the values a bit in the right direction. And the brighter the pixel is, the more you have to move. This is like the stupidest thing you could imagine again. Does it work? Well, it can possibly work, and actually it can. What you see on the right is the picture we saw earlier, where we said this is the ideal 3 minus the ideal 7. So the right one is sort of the perfect thing. And on the left is how the system evolves just by giving it a letter, saying, well, is it right? Oh, it's wrong, then I'm going to twist all these values a little bit like this. Or if it was right, I'm going to twist all the right values a little bit and change them a little bit. And within, I had to slow this down because it does this within a millisecond. It comes up with the picture on the left, which is very comparable to the picture on the right. But of course, we made it in a very stupid way. So how good can it be? Well, it's actually better than the one that we made, which is irritating. And actually, if you look at the differences, the ones it gets wrong, you're like, yeah, I would also have gotten that one wrong. So we now have made a decision rule that is based on just, yeah, if the value was good, make the value a bit higher rule. That was it. And it can now differentiate a 3 and a 7 better than most people. It's terrible. This really is the magic. So whenever ChatGPT learns through reinforcement learning or whatever, this exact same procedure applies. It says these are the neurons that we liked, that contributed to the right answer. These are the neurons that we did not like. Those values are going to go up. Those values are going to go down. That really is it. So a little bit on terminology. They call this the loss function. And the loss function pops up everywhere in the sense that people that are into deep learning, they will say, minimizing the loss function is the goal of my life. And the loss function is how wrong you were. In this case, you say, well, our decision rule was R is bigger than 0, then it's a 7. In neural networks, they always use the loss function, which means you say, well, if it was a 7, then we want the outcome to be 1. And if it's a 3, we want the outcome to be 0. And if the actual outcome is like 1/2, is a half, 0.5, then we're 0.5 away from where we want to be in this case. And this is how you aim all the optimizations so that the loss function goes down. So whenever it talks about a loss function, it's nothing other than how wrong am I? Now, real digits. Because doing a 3 and a 7 is not actually that hard. And there are 10 digits. And as you can see, many of these digits actually are not that dissimilar. So the 1 and a 7, and yeah, they're actually quite close. And we have hundreds of thousands of digits to test with. So it's good. Later we'll find that these are all American digits, and that no matter how hard you train your network on American digits, if you encounter a Dutch person that writes a 7 differently, it's not going to work. Because the network did not really learn about a 7, it learned about an American 7. By the way, not knocking the Americans, because they did make this database, and here in Europe we did not. So it's relatively our own fault. So, but here you can see that life is a bit more difficult. When we zoom in a little bit, yeah, I'm not sure if you know what this letter is. I'm not entirely, I think it's an A, actually. But so this is a bit more challenging stuff to learn, and we cannot do it using the simple 3 and 7 rule, for the simple reason that we have more than 2 outcomes. We have 10 outcomes now. So how would you do that? The first thing these people do here on the left is what the image would look like, 28 pixels like that, 28 pixels like that. That is how I would think you would process an image in neural learning and neural network. That's not what they do. They always flatten it in the start. And that's in a way silly, because that means that you now have 784 pixels, but they no longer are really related to each other. But this is how the simple networks work. And then you multiply them by one honking matrix. 128 by 784 numbers. And out comes another matrix. And you multiply that by another one. And you multiply that by another one. And out comes a matrix with numbers 1, 2, 3, up to 10. And it's nice because we had 10 digits we want to recognize. And this is the 10 outputs that say which network, which digit the letter thinks it saw. So in the end, you see all kinds of different matrix operations, and in the end, the small matrix comes out with the conclusion. So that's like really nice. And one reason that people sometimes ask is, why did we suddenly get all these super smart networks? And why did it take so long? Because this is 1989 technology. The network you saw here has 3 layers. Back in the dark ages of neural networks and machine learning, someone had proven that it was not necessary to have more than 2 layers. It's a very good mathematical proof. There is nothing wrong with the mathematical proof, except that it comes with a lot of constraints. Where it says, yeah, under these conditions, you will never make your network any better with more layers. And I think that set back the industry for like 10 years. Until someone reasoned, well, actually, we can do something and have more layers and do more things. And one of the things they discovered is that if you take 3 matrices and you just multiply them all by each other, you actually have built one big matrix. Because there are only linear elements in there, so you have not invented anything new. And then at one point, people said, well, what about if we use the rectified linear unit? It sounds really, really good. In this field, they love inventing special terms. And the rectified linear unit is, well, maybe if the number is below 0, we turn it into 0. And if the number is more than 0, we leave it alone. That's the rectified linear unit. And what if we put that in between the matrices? That generates a non-linear element, which means that you can start creating if-else kind of rules and constructs. And that was a sort of a really big breakthrough. And then, like, I think 7 years ago, someone said, well, maybe it's too boring. Let's do the Gaussian error linear unit, which is not Gaussian, it's not an error, and it's also not linear. But they decided to do it anyhow. This was invented by Google, and they put it in Google Bert. It's nice, my name is Bert. Google Bert is one of the, they call it BERT, but they get it all wrong. That's their very impressive neural network. They said, well, what if we use this Gaussian error linear unit that is sort of a bit more bendy? And they did it, and everything became better. And to this day, we do not know why. This is, again, a recurring theme. In the machine learning business, they just, right now we're still at the stage that if you just try some random things, they very often work. And if you then ask, yeah, why does it work? You're like, I don't know, just do it. It's working really well. And you can ask ChatGPT, it's really fun to ask ChatGPT about its own life, and it will sometimes tell you useful things. So, but in any case, you put these non-linearities in between, which means that you can have a really sort of expressive programming language where these matrices turn on and off. For example, to differentiate between a 5 and a 7, this might say, well, for a 5, you need to focus more on this bit of the screen. So this is what it eventually looks like. It's not that hard, but it's still rather simple, actually. This is just a bunch of matrix multiplications and changing negative numbers by 0. And out comes this matrix below from 1 to 10, and that tells you which digit the network thinks it is. And just to make life a little bit more complicated, they invented a new term, the soft log match. A soft log max, even. And what does that do? Ah, the math looks so good. And it looks really good, and actually if you try to implement it like this, nothing will work. But it looks so good. You need to simplify it to the one on the right, because otherwise you get all kinds of infinities, and then your network only works on the demo, which is also a key point of neural learning. What it does here, it says these are the 10 digits, 0, 1, 2, 3, 4, 5. And in this case, it's clearly a 5 that it saw because it has the highest input value, a 4. If we then do that logarithmic thing up there, it becomes minus 0.05. And that is the exponential of the chance that it is a 5. Dus with this, the network says, I am like really sure that this is a 5. This is another key thing. If you're interested in doing some machine learning, see if you can get the output of the soft log max. Because that not only tells you the network thinks that this is a cat, it will also say, well, I'm not that sure. It could also be the sheep or whatever. But this is actually more interesting than just the verdict. Now, what does it look like in code? And in code, it's actually a lot easier to look at. First, we flatten the image. Then we have a linear combination 1 through which we forward the numbers. Then we do this rectifying linear unit. We forward it again, rectified linear, we forward it again, soft log max. And then the loss function is the expectation. So we know that this is a 5. That means that we can write a matrix that says, well, put a 1 in the 5 position. We multiply that, and then we get the loss. So this is the whole description in matrix terms of a neural network that can recognize digits. And it's shorter in code than it is in pictures. Now, does it actually work? Remember that to improve the neural network, and this is a real key point, so you can just snooze off for the rest of the meeting, but this is a key point. I said that the dumbest way of doing it is just twisting the knobs a bit in the right direction, which is simple, relatively simple, if you have this formula. Because you know, if you twist the W1 knob upwards, the answer will also go upwards. But what about if you have this huge thing? What changes to the output if you only change this value a little bit? What happens? It's a very difficult calculation, or at least it's a very complex component. It is not difficult to do, but it's just a ton of work. Many years ago, decades ago, someone figured out that you can make your compiler do all this work for you. And that is, without that invention, this would all be nearly impossible. Because you wouldn't know which way to twist this knob otherwise. I have a very pretty picture of this, and probably going to leave it at that. But it's good to realize that this simple digit recognizing neural network already has over 100,000 weights attached to it. So there's no chance in hell that you're ever going to figure out by hand which one you need to change. So how are you going to do that? With this very pretty picture. You will recognize maybe that this is how you parse the formula down below, what that looks like. And it turns out you can do all the differentiation that you need to this using this representation of the whole 100,000 parameters in the network. And then that looks like this when you calculate the gradient. It's like real pretty, and here I'm going to refer you to the blog post on autogradients to really figure out how it works. But without this process, nothing in this scene would work, because you would not be able to calculate how to train your network. So this is another thing you will hear about. To get the loss function to 0, which means that the network provides the good answers. Every training round, we twist the knobs a little bit. But by how much shall we twist them? If you play it safe and slow, you will only twist them a little bit. Because if you twist them too much, you might zoom past the right answer. So when you're conservative, you make it go slow. The problem is, if you do that, your network might take like 3 months to train. Or 6 months, and you will only find that out after a few months. So you need to go faster than that. You want to do more clever things. And this is called the gradient descent with momentum. And this was the best way of doing this was originally described in a halfway published paper by Google called RMS prop. And they never got around to really publishing it. But that was sort of an optimum way of figuring out by how much should we twist these knobs. Everyone has now settled on a system called Adam. And again, we don't really know why it works. And there is some meta-research going on that says, okay, if you twist these knobs with momentum like this, it has been found that networks sort of generalize a bit better. And if you use Adam, they get to their destination faster, which means you can spend more time doing optimization and eventually still get a better result. But underwater, you will often see people say, yeah, then we do Adam. Well, Adam is not your friend, or maybe is your friend, but that is these kinds of algorithms. And it's also important to know, you can see from this, when the arrow sort of tries to optimize, it nearly gets stuck up there. If you see a demo online that says, hey, we're going to train this network and it's going to recognize cats and dogs and it's going to do so in 5 minutes, in real life, when people try training that network, it got stuck all the time. And then people change the conditions a little bit, change the optimizer, or make it go a little bit faster, and then it works. And that's the blog post that they publish. They did not publish the fact that for 3 weeks the whole network did nothing. Which is not fair, but I'm telling that because I wrote this stuff myself, my stuff gets stuck all the time. And then I spoke to professional people, they said, yeah, we're same here. But we don't want to bore the readers with that. So it's not you. But gradient descent is a very important topic. And now you know that if someone says they're using Adam, then that's this. Now, how good is this simple network that we made? Because we wanted the network to recognize 10 handwritten digits. And this is the classical graph that you make of that. That says, okay, these are the batches. We're going to get to that later, what that is. And we have split the digits into 2 groups. We want to prevent the network from just memorizing what the digits look like. It means that we take a subset of the digits and we never show them to the network. It can only train on the other set. Sometimes, if your network is just memorizing the training set, then it will suck on validation. But here we can see that after 1,000 batches, this very simple solution got like 90% of the digits correct. And if you recall what the digits look like, it's not so bad. So should we feel good at this result? And many people would feel good and now publish a blog post and say, hey, I built a 200-line thing that can read handwritten digits. Well, this is the so-called confusion matrix. And I love this one because it's very confusing. On the left, it shows the real digit. And on top, it shows the digit that the computer thought it was. And here you can see that most of the time when it gets a 5, there were 3,548 times when the network saw a 5, and it also actually was a 5. So this confusion matrix allows you to see when a network was wrong. If you read any other people's neural network deep learning stuff, always ask for the confusion matrix, because it tells you a lot. And this is, for example, very important when recognizing spam, because you are far more worried about real messages that look like spam than the other way around. So this thing answers the question, is this of any use for me? Now, should we be celebrating this network? Not really. This is the performance of the network if we shift each digit a little bit and add a little bit of noise to it. And the network immediately, the performance went down from like 90% to 50% maybe. And this shows you that this was not really a learning network because it got confused by a few flipped pixels. This process is called data augmentation. So, and what you do with that is you take your training data and you change it in ways that no human being would be fooled by rotating a little bit, making it a bit bigger, moving it around, adding some noise. And if you see a network that immediately collapses on that, you know, well, it was not actually a good network. And there's a good reason for that, because the network that we built really wants the digits to be centered exactly in the middle. I told you this was the hello world set of neural learning. It is the hello world set because everything is perfectly in the middle and the intensities are just right. So if you change only a little thing, the network goes like, oh, oops. And this is the constant fight you will have if you do real machine learning, that you will very soon have a network that actually does some nice things until you flip 3 pixels. And again, that does not make it to the demo that you saw on YouTube where someone clicked together in 5 lines a script that will recognize cars. Except it will no longer recognize the car if you add 1 pixel. And these are the rules. And I want to sort of entertain you with this, but I also have an extremely serious message. If we start using machine learning in places where it really matters, like for example, we say this is a fake driving license based on our detection, or this is a fraudulent transaction, stock transaction. So these are cases when it really means something. Whatever you build, very soon, pleasingly soon, you will have something that works on your data. And it's a great feeling. You sit there, well, hey, I built my machine. And it recognizes stuff, and it's wonderful. And then you try it on some validation data that the system had not yet seen, but it's still the same sort of data that you originally had. It's just data that the system hasn't seen yet. And the results are terrible. The results are just terrible. So then you fix it that it works on the data that it has not yet seen. And then you give it to someone else. You say, hey, can you also use this on your banking transactions? And again, the system fails miserably. Why does it fail miserably? There were lots of hidden assumptions in your validation data even. Because your data was just always, the transactions were timed at the whole hour. And in the training data, if in the other people's data, it's all centered on the whole minute. And secretly, your neural network learned from that. Because we do not know what the system is learning. We only know its results. We have so many parameters, we don't know what they mean. So after a lot of disappointment, you get it to work on other people's real data. And the fourth step, that's even the most difficult one, they get it to work on their data. Because there are so many ways in which you might secretly have been helping the system along that you didn't know. Most people are like, the project is done at phase 2, and they start celebrating. And then all of a sudden it's incredibly disappointing when all the wrong hospital appointments get cancelled. So you should be extremely skeptical. And the more impressive your results are, the more skeptical you should be. So I have some parting thoughts. And let's the show of hands maybe. Who here thinks that can AI answer really difficult questions? Do you know? It depends on the question. Are you afraid for your job because of AI? You're all wrong. Let me tell you that, because I see almost no raised hands. The reality is really that many of the things that we as human beings do, we can of course always say, yeah, I saw ChatGPT do this, but I could do this better. And it's probably true. But 95% of the world could not do it better. And there are many use cases where we might know, hey, we could do this better, but where the people in charge of companies go like, well, maybe you could do it better, but the ChatGPT doesn't whine about working hours and stuff. So I've been studying this for a while, and I'm like super worried, not just for my job, but mostly for the fact that people will just ignore this wonderful page and just start doing it. And especially on HR kind of things, where who are we going to hire? You can very quickly give resumes. I tried it. You can give resumes to ChatGPT right now, and it will already tell you which is the best one. It doesn't mean that it's right, but it will give you an answer. It might not be the one you like. So the deep learning achieves some rather really magical results. I also tried it on a database like with email messages and say, can you recognize threatening email messages in there? And without any further work, it picked up 3 email messages where it says, I think these are threatening, and it was right. And actually with the third one, it says, yeah, I'm not sure, it depends a little bit on the context. And then I had to go for a walk, because it's like extremely depressing to see your computer do that kind of thing. But the other key thing is, we are not yet lost. This is not only magic coming out of the NVIDIA chip in the cloud in California or in Seattle. So far, this stuff is very difficult, but the people doing it are not magic. And as I told you, many of the things they are doing right now are still sort of, hey, let's try this, and wow, it works. That means we can still get on board. There is still time to say, hey, I want to understand this technology, I want to make this my own, and I want to use this in my own code, but not by doing import super duper magic, but by having a library that I really understand and that I can trust, that I can inspect, that I have metrics for, and that we could use this to improve our own stuff without giving up our autonomy. Because if you write a big bit of code right now that has import OpenAI in there, and then it opens up 25 sockets to the cloud, that's not your code. That's someone else's code. And what I really would like to hope, and that's the note on which I would like to, for now at least, end this presentation. One of my favorite pieces of technology in the world is SQLite. Because SQLite is sort of the Rick Astley of databases. It will never give you up. It will never let you down. It will never leave you. And because this is literally true. SQLite will never go away because it's one single source code, one single file of source code, and I can always use it. It has a license which will always allow me to use it, and I can be confident in knowing that even 20 years from now, I will still be able to rely on it, or the software that I developed will still be able to run. However, if I base myself on the latest and greatest machine learning stuff, it will not work by the end of the year, because everyone has changed the APIs 5 times, and now suddenly there's a huge license fee to use the API. One of the things I would really like to hope is that sort of actual programmers pick up the mantle and say, hey, we want to understand this machine learning stuff and bring it back as modules that we can really understand, use in our software, and feel like they are our own. Like we can feel that SQLite is our own, and that we are not fully dependent on libraries from far away. Meanwhile, you can of course have a lot of fun using these libraries from far away, but know that one day there will be an API fee and suddenly your whole business model is down the drain, as we see happen with Reddit lately, for example. I can tell you all the free AI stuff will eventually go away. So it's really important that as many people as possible understand how this works. And with that, I'm done. There are some useful links here. And again, don't copy-paste this stuff. Whisper.cpp, I need to mention that one. If up to now you were like, yeah, this stuff is not so real, Whisper.cpp, you can download it on your own computer, compile it in one command, and then you can talk to your computer in Dutch, and it will transcribe it for you in English. And this is a real computer program in one directory. You can run make, you can see it, you can investigate how it works. And it will understand, I think, 95 languages and translate them all into English for you, sometimes even when you don't want that. So I did some testing with it, and I had one English phrase in what I was saying, and it secretly translated that into Dutch already. This Whisper.cpp is so compact that someone ported it to a simple iPhone app, where your iPhone does this stuff locally and on the phone. I've been testing it in bars, in noisy places, and it just does that. But you can clone that GitHub repository, run make, and it will work for you. And this was what, for me, made it clear that, okay, this is technology that we can also own and not just get from the cloud. There's a Llama GPT-like thing. The real ChatGPT is censored. It has all these kinds of rules. It will not tell you how to make an atomic bomb, for example. It's sad. The Llama thing from Meta will explain you in great detail how to build a hydrogen bomb. And it's enthusiastic about it even. And you can, again, compile that yourself. Deep learning, totally from scratch. There is hope. You can hopefully find some hope on this page. And with that, I'd like to thank you for your attention.